This video is meant for my students who missed rate expression last week. Okay, rate expression is an equation to show exactly how the rate is dependent on concentration of reactants. So for example, if I have A plus say 3B, you get 2C's and a D. And rate expression looks something like this. Rate equals to K, concentration of A, maybe squared, maybe not. And these figures here, you cannot get it from the stoichiometry. Okay, so you can't obtain this, it cannot be deduced from the stoichiometric equation. Okay, where will this rate expression come from? The rate expression can only be obtained experimentally. It means someone has to run an experiment, then you'll be able to know what is the rate expression. Okay, the rate expression that you have here, or this equation that you have here, it might not include all of the reactants. Sometimes even if you have, say, an E here, you might not see it here. There might not be an E here. We'll see how it is later. We focus on just a simple rate expression first. Okay, now this 2 here, or squared here, this is called the order of reaction. So at this point, you just need to know what a rate expression looks like and what are the meaning of those clauses here. So this is just rate of reaction, which is in mole per dm cube, say per second or per minute. K is the rate constant. Okay, so you just need to know what it is for now. A and B, we put a square bracket there, which means it's concentration in mole per dm cube. And the little numbers, the square or cube or whatever, that is the order of reaction. That is the to the power of. Okay, and this power of, you cannot get it from the stoichiometry. You have to run an experiment to find out what it is. Okay, let's do a little exercise on how to get the units of rate constant. Don't worry about the other things first. How this equation come about, how they run the experiment, it's a separate video from this. Okay, if I have a rate equation or rate expression like this, what would my K unit be? And if I have a rate equation like this, what is my unit? If I have rate equals to K A squared only, or if I have rate equals to K A B, what is the unit of my rate constant? Let's try that first. Rate is in mole per dm cube per second. K, we're trying to figure that out right now. And this is in mole per dm cube, and it's squared, and another mole per dm cube. So looking at this, you can figure out what is the unit of the K, right? Okay, this is an easy one. And then I have this. So rate never changes. Rate is just mole per dm cube per second. But K, the unit always changes. I'm going to separate this two. Mole per dm cube and another mole per dm cube. Rate never changes. It's mole per dm cube per second. And K, and this is mole per dm cube squared. Okay, tackle the easy one first. So cut. So this, the K, the unit for K is per second. Okay, let's do another easy one. So cut, bring this down. So K is in per mole, dm cube per second. Okay, if you haven't noticed, so you have one concentration here and another concentration expression here, and this is concentration squared. You're gonna get the same answer. So mole per mole, dm cube, and per second. Okay, so for this, you get the idea. So cut one of them, you're going to bring this down. So K per mole twice, and then dm6, and then per second. So you see the per second is always there. Per second will always be there because rate has a per second and concentration doesn't. Next, let's see what what do those orders mean? Zero order, first order, and second order. So zero order means the rate is not dependent on that reactant. So for example, if I have A plus B, I get C plus D. I'll just put some random numbers here. Okay. So then if let's say my rate equals to K, so you can't get this like out of nowhere, okay? Someone will have to give that to you, or a student must run an experiment to get what is the rate expression first. Okay, so for example, if I have this rate equal to KB squared, and you don't see A there. So if I want to plot the graph of rate on this side, and I want to plot A on this side. Okay, do you notice that A is not in this rate equation? So if I change A, so A from low A, medium A, very high A, there's no change in my rate of reaction. Therefore, it's going to be straight all the way. So here, rate only depends on the B. It doesn't depend on the A. Okay, what if I plot another graph here? I want A versus time. Okay, do you remember that this graph of concentration and time here, x-axis time and y-axis concentration, the gradient of this graph, like you've seen this in IG, the gradient of this graph represents rate. Now look at this, the rate didn't change. No matter what the concentration was, the rate was the same. What does that tell us? It means that the gradient of the graph on the right must be the same all the way. So like that. Same gradient here, same gradient here, same gradient here. So it's something like if I plot, okay, at a high concentration, the gradient is this. At a high concentration, the gradient is that. And maybe at a slightly lower concentration, the gradient is still that. A lower concentration, gradient is still that. And if I go lower concentration, the gradient is still the same. Okay, that's what it means. So this is if rate is not dependent on the concentration of one of these reactants. Okay, now example of a first order reaction. So A plus B equals C plus D. I'm just going to put some random numbers here. Okay, and rate equals to K A B squared here. Just vary my examples here. Okay, so if I were to plot rate versus C, this means that I'm ignoring B. B must stay constant and not change in the experiment. So I'm only plotting rate with A. So don't do anything with the B. Rate is directly proportional with A, right? In the equation, in the rate expression that you got. So in that case, you will get this going up. Okay, like that. And the same thing, if I'm gonna plot the concentration of A versus time, okay, you see that the rate increase, which means the steepness on this graph here must change. It's not constant. It's not like the previous graph. Okay, so let's see. At high concentration of A, so this on the right side means high concentration of A, right? And on the left side here is close to zero, means lower concentration of A. Okay, so at high concentration of A, my rate is high. So at high concentration of A, my gradient must be steep. At medium concentration of A, my rate is slightly lower. So at medium concentration of A, it must be less steep. And then at a much, much lower concentration of A, uh, the rate is much, much less. So it must be much, much less steep. So overall, my graph should look like this curve down. Okay, now the special thing about the first order reaction is that the half-life, what is a half-life? So if this is 1 mole per dm cube, for it to drop to 0.5 mole per dm cube, the time taken should be the same as if from 0.5 dm cube, 0.5 mole per dm cube, sorry, to drop to 0.5 drop to 0.25 mole per dm cube of A. So this time must be the same. Okay, so these both are in mole per dm cube. Okay, so this we call the half-life. The half-life is constant. I'll just skip to the expression of the half-life. Half-life is ln 2 over k. What k is this? It's k that we were calculating just now, the unit. We were figuring out the unit just now. So there will be questions where you calculate the k as well. So if you've got the value of k, you will know how long it takes for it to drop from 1 mole per dm cube to half mole per dm cube. That is the half-life. It's not dependent on how concentrated it is because you don't see a concentration clause inside here, right? So no matter what the concentration is for a first order reaction, you'll see that the half-life remains the same. It's always the same. You just take ln 2 over its k. Okay, that's for first order reaction. Let's look at second order reaction. Okay, example 2A plus 3B. It's B plus B. Let's say this is the stoichiometry, random there, and rate equals to Ka squared. Let's say that's B, doesn't matter. Okay, how do I plot rate versus A? So it's exponential, right? So the graph should go this way. The rate increases much more as the concentration increase. But what does that mean? Like if here's 1, yeah, here's like kind of 1. And then if here's 2, then here would be like 4. And if here's 3, and this would be 9. Oh, something like that. Okay, just imagine it. We just put some figures there to imagine what it looks like. 4 and then 16. Okay, how do we plot? Do we plot A versus time? So at high concentration, the gradient is very much higher. And at low concentration, the gradient is very much lower. That sounds familiar. It's a little bit like the first order graph. Okay, it's gonna look similar, except that it's exponential, right? Except that the half-life is not constant. Oh, I think I'll redraw that. Maybe. Okay, so it still coincides with what we said just now. At high concentration, the gradient or the rate is high. And then at medium concentration, the rate is slightly lower here. So medium concentration is lower in its gradient. It's slightly less steep. Then at very much lower concentration, the rate is much lower, which means the gradient here will also have to be much lower or less steep here. Okay, but the thing is, how's it different from the first order graph? The difference is that you'll see the half-life here when it's concentrated, when it's very concentrated, when A is concentrated, the half-life is a shorter time. And when the concentration has decreased to this point, it takes longer time to drop to half. So this is like 1 mole per dm cube, and this is 0.5 mole per dm cube, and the next one is 0.25 mole per dm cube. So for it to drop from 0.5 to 0.25 mole per dm cube, it took a longer time. So this half-life is not the same. Okay, so not the same. The first half-life and the second half-life is not the same. Well, what is it dependent on? It's dependent on the concentration. So if you look at the half-life equation here, it's not the same as the one for first order. For first order, there's no concentration in its half-life equation. It's a constant, ln 2, over k, which is also a constant. So you get a constant half-life. For second order, the concentration of A is in there. So the half-life is dependent on the concentration of A. If the A was concentrated, the half-life will be shorter, which makes sense, right? The more concentrated A is, the lower the time taken, which means the faster the rate of reaction. And over time, concentration of A has decreased, therefore time taken is higher now, which also makes sense, right? So lower concentration, slower rate of reaction. That's why higher time. Okay, how we're gonna use this zero order, first order, and second order and relate it to what we have learned, that will be in the next